Hey everyone! Today, we're diving into a fascinating and critical topic: how interplanetary shocks that hit Earth's magnetic field can affect our infrastructure. Scientists have discovered that these shocks can generate powerful ground-level electric currents, posing threats to pipelines and submarine cables. Let's break down what this means and why it matters. Welcome to Trendstorm. Chapter 1. Auroras and geomagnetically induced currents. We all love watching the mesmerizing auroras, but did you know that these beautiful light shows are actually a sign of powerful space weather events? Auroras are caused by particles from the sun hitting Earth's magnetic field. While they're stunning to look at, these impacts also cause geomagnetically induced currents, GICs, at ground level, which can damage our infrastructure. Chapter 2. Understanding interplanetary shocks. Recently, scientists have made a significant discovery regarding interplanetary shocks. These shocks, which can compress Earth's magnetic field, generate GICs that can damage infrastructure. The key finding is that the angle at which these shocks hit the magnetic field determines the strength of the currents. Shocks that strike head-on are much more powerful than those that hit at an angle. Chapter 3. The research findings. Researchers, including Dr. Denny Oliveira from NASA's Goddard Space Flight Center, have published their findings in Frontiers in Astronomy and Space Sciences. They compared interplanetary shocks to real-time measurements of GICs, showing that head-on impacts produce stronger currents. This research is crucial for forecasting potential damage to our infrastructure. GICs can damage various infrastructures that conduct electricity, such as pipelines and submarine cables. For example, during a severe geomagnetic storm in March 1989, the Hydro-Quebec power grid in Canada was shut down for nearly 9 hours, affecting millions of people. Even less severe, frequent shocks can gradually damage infrastructure over time. To understand the effects of these shocks, the researchers analyzed a database of interplanetary shocks and cross-referenced it with readings of GICs from a natural gas pipeline in Mäntsälä, Finland. They found that nearly frontal shocks caused higher peaks in GICs both immediately after the shock and during the following substorm. The time of day also played a role, with more intense currents occurring around magnetic midnight. Chapter 4. Predicting and protecting against shocks. One of the most promising aspects of this research is that the angles of these shocks can be predicted up to 2 hours before impact. This means we could potentially set up protections for our electricity grids and other vulnerable infrastructure before the strongest shocks hit. Dr. Oliveira suggests that power infrastructure operators could manage specific electric circuits when a shock alert is issued to prevent GICs from reducing the lifetime of the equipment. Chapter 5. Need for more data. However, there's still more work to be done. The current data was collected only at a specific location, and there are gaps in the data. Scientists need more recordings of currents at different latitudes to fully understand these phenomena and provide more comprehensive protections. This discovery is a crucial step towards protecting our infrastructure from the damaging effects of space weather. By understanding how interplanetary shocks impact Earth's magnetic field and generate geomagnetically induced currents, we can develop better strategies to safeguard our critical infrastructure. Source: Frontiers in Astronomy and Space Sciences. If you found this video informative, make sure to like, subscribe, and hit the bell icon for more updates on the latest scientific discoveries and their implications. Let us know in the comments what you think about this new research and how we can better protect our infrastructure from space weather events. Thanks for watching, and see you in the next video.